In the last lecture, we introduced the concept of a transmission line and talked about how we can model a short length of the transmission line, speaking specifically about how if you have the voltage here and a current here at Z, and you wanted to see what was going just a little bit further on, one of the non-idealities is that you have a series inductance, which kind of prevents the current from changing immediately, and you also have a shunt capacitor, which prevents the voltage from changing immediately, and then they also have associated sources of loss associated with it. So in terms of the series, you call it R. In terms of the shunt, you call it G, and then you have your L and your C, and then through that we wrote. So when you apply Kirchhoff's voltage law, you arrive at partial differentiator of the voltage with respect to position is going to be equal to minus Ri minus L di dt. And then similarly for the current, you have di dz is going to be equal to minus GV minus C dV dt. Now, what we want to try to do for this particular skill is to understand what the basic general form of a solution that simultaneously solves these two equations are. Now, one of the main challenges when you're trying to guess a solution for this is that in this equation you relate the voltage to the current, and in this one you relate the current to the voltage. So what we want to get to is to have just a single equation represent with just the voltage being the variable, and a single differential equation with just the current. And that way, if depending on how it looks, we might be able to do our tried and true method of guess and check to come up with a general form for the solution. Now, one cop-out to make things a little easier, just so that we know what the solution is going to look like, is let's just assume this is lossless. So let's just assume that no energy is lost through this resistor and no energy is lost through this path. So this is actually a nice little open circuit that we don't have to worry about. And so what that means is that we don't worry about the R anymore, and we don't worry about G anymore. And this is why we use G instead of R for the series, so that when we want the ideal lossless case, we just set the associated variables to be equal to 0. And so that now gives us dV dz is going to be equal to minus L di dt. And also we now have di dz is going to be equal to minus C dV dt. Now, one trick that we can pull is if we have dz dt on the right-hand side of both equations, then we can apply some substitutions. So let's take both sides by dz. So now you have the second derivative of v is equal to minus L di dt dz squared. So now you look at this and you say, wow, it sure would be nice if I had a di squared dt dz over here that I can then use to substitute. So we can make that happen. We just have to take this equation and add a d by dt to it. So we're going to take this equation and add a d by dt. So now we have d squared dz dt of I is going to be equal to, and then you now have d by dt, this side, so minus C dV dt. Oh, and now it's the second derivative of dV relative to time. So now this gives us a nice little opening to substitute. So we're going to substitute this quantity in there, and now we're going to have dV now we're going to have the second derivative of v with respect to z is going to be equal to LC d squared t squared v. So So now we have d by dz squared of v is going to be related to d by dt, second derivative of the voltage with respect to time, through a factor of LC. And similarly, we can pull the same trick with the current. So if we start with this equation now, we had di by dz is equal to minus c dv dt. And then we're going to change this into second derivative with respect to z. So that gives us this dt dz. Well, we say, well, that's if we just take this and add a dt, we can have something nice that we can substitute. So we take this equation, add a dt to it. So again, it's going to give you minus L di second derivative of I. So now this gives you something that you can substitute in, and then you come with our current only equation. It's going to be equal to LC di squared dt squared of I. So now this is kind of a reorganized form of the transmission line equations, except now you, for the low price of adding an extra order to the differentiation, you are now left with one variable. And this is now something that you can do a guess and check on to come up with the solution. So let's just rewrite that, give ourselves a little bit more whiteboard space, and summarize our basic equations again. So we have dv dz is equal to minus L di dt, assuming that things are lossless. And then we have di dz is equal to minus c dv dt, again assuming that it's lossless. And then through a little bit of manipulation and acrobatics that I just erased, we now have d by dz squared of v is related to the second time derivative of v by this factor LC. And then it turns out that the current also has this same relationship. So d by dz squared of I is going to be equal to LC d by dt squared of I. So for the sake of having something to refer back to, I'll call this equation 1, equation 2, and then the second pair, equation 3, and equation 4. So now we can do the glamorous guess and check approach to figure out a very general form of the solution. And so using a little bit of thought and generalization, we can see that you can have a solution that takes the form of some kind of a forward propagating wave and some kind of backward propagating wave. So the forward propagating wave, we'll say, has a magnitude of f plus, and then its shape will be defined as this function f, which will be used to represent the forward propagating wave, t minus z over vp. And then the backward propagating wave has an amplitude of v minus, and then we'll use g to represent the shape of the backward propagating wave, t z over vp. Now this vp is a propagation velocity. So vp is the velocity. And you can see that because vp is a factor that represents the time and the location of a particular point in phase. And if you go back to what we're going to find if we plug this in and do some math is that you'll see that the propagation velocity is going to be equal to 1 over square root LC. And then we'll also define another quantity similar to what we were talking about before, but the impedance of the transmission line is going to be the square root of L over C. Now remember, these are all per unit length. So L over C, L is still Henry's per meter, C is still Faraday's per meter. And And so keep that in mind because we don't want our quantities to be dependent on how long the transmission line is. Now, one of the things, how do we know that this is a forward and backward propagating wave? The key part is the signs between the t variable and the z variable. So if they're opposite signs, that means that as time increases, the wave shifts over to the right, and if they're the same sign, then that means the opposite. So again, you can use the opposite. So if the variable, the coefficient between t and z have opposite signs, that's going to tell you that it's a forward propagating wave, as in it's propagating in the positive z direction. One of the things that you'll see is that this thing will solve equation 3. So if we just eyeball it, if we look at what d squared of v is going to turn into, you're going to take the derivative of this twice. When you take the derivative of z one time, you're going to multiply this whole thing by a minus vp, and then when you take it again, you're going to multiply it by another minus vp. So what you're going to end up with is 1 over vp squared of the same thing, right? So over here, you also get a 1 over vp squared. You're going to factor the whole thing out. So you get 1 over vp squared v of zt, which if you look over and take the derivative with respect to t, the coefficient with respect to t is 1, right? So d by dt squared v times LC is going to be, so if you take the time derivative twice, you get the same thing, right? Because the coefficient here is equal to 1. So you get LC v of zt. And note that because when you plug in that relationship, this is 1 over square root of LC, which is equal to LC. So voila, the two sides are equal. So this is a general solution to the transmission line equation for voltage. And now, so the next thing that you want to know is, how do I get the current? So to get the current, if we call this, let's call this equation 5, we're going to plug equation 5 into equation 2, which tells us how to change it into current. So di, and then we're going to integrate to find what the current is. So it's going to be equal to minus c, and then the derivative with respect to t, again, kind of like what we talked about here, since the coefficient for t is equal to 1, it's just going to be the original equation. V plus d by dt of f t minus c over vp, and then also minus backward propagating component, so d by dt g of t plus c over vp. And as you see, the integration, the derivative of this with respect to time and that with respect to time, d by dt of f is equal to f, d by dt of g is equal to g, and so we actually don't have to worry about these. And that's the backward propagating wave. And so now to get the current, you can just take the integral with respect to z symbolically. So I is going to be equal to minus c, and then when you take the integral, you're going to get this extra factor of negative the velocity, v plus f of t minus c over vp. And then the same thing here. You're going to get minus c, but now there's no minus sign here, so you're going to get a factor of Vp e minus g of t plus c over Vp. And now this looks like doesn't really mean very much, but if you use the fact that c Vp is going to be equal to, remember, Vp is square root of L over C, right? So that's equal to square root of L over C. And so that's going to give you square root of C over L, which is going to be equal to 1 over Z naught. And so if you plug that in, you're going to see something that makes a little bit more intuitive sense. Which is that they differ from the voltage signal by a factor of Z. So this is kind of like saying, hey, Ohm's law still works. Now, one of the things to pay attention to that tripped me up for a long time is that the current, the backward propagating wave in the current, now has a negative sign. And if you think about that, it looks kind of counterintuitive, but it does make sense when you think about it, because if you have a voltage that's going this way, the voltage is positive when you measure it here, and it's positive when you measure it on that side. But when you're actually, when the wave is going backwards, you still have a positive wave that's propagating to the left, but now the current is actually flowing in the opposite direction, in the negative Z direction. And so note that for the current, the backward propagating wave is actually has a negative sign. So really remember that. That came back to bite me on numerous occasions. Now let's wrap up by doing a little bit of a conceptual exercise by looking at a specific solution. So let's just say that I'm describing some waves on a transmission line, and the equations for the voltage is going to be A, and then it's some function. We don't really worry about what it looks like, but 2t minus z plus some other function, some other wave, 4t plus 3z. And then the corresponding current for this equation is c, and then this other function we'll call little c, 3t plus 2z minus d minus 2t minus z. Now, one of the things that we'll note is that as you can see between here, this is a forward wave, and this is a backward wave. And we can tell this two ways. One is because these have opposite signs, and here t and z have the same sign. The other telltale sign is that for the first term, the current is positive, it's going in the positive direction, but the second term, this is actually negative. The other thing that you'll be able to pull out from if you were given these two equations is the velocity. So to find that, you would rewrite it. You can rewrite it so that it fits the form of the t minus z over Vp. So to do that, you would factor out the 2, and that would give you t minus z over 2. So that tells you that the velocity of the wave, of the forward wave, is going to be 2. The other thing is that, so you can also find the velocity, you can find the direction, and then the last thing to point out is that you can also find the characteristic impedance of the material. The characteristic impedance, Z naught, is going to be just like Ohm's law would suggest. So the voltage over the current, A over C, which should also be equal to B over D. And since these are propagating in the same material, these have to be the same. Otherwise, this equation doesn't work, and it's not propagating through a real medium. So there's a series of ways that we can also assess your understanding of these general solutions by giving you equations like this and asking you questions about what information you can glean about the forward or backward propagating wave based on the equations given here.